Welcome to today's colloquium. So today's speaker is Professor Miao from the UCAS, that is the University of Chinese Academy of Sciences, which is very close from here. And he's a theoretical physicist and working on the equilibrium and non-equilibrium systems. And I'm very happy to have Professor Miao today. He obtained a PhD at the Chinese Academy of Sciences in 2006. Yeah. Then he did a postdoc in Canada, also Germany, and then he came back to UCAS. So today he will tell us about the equilibrium and non-equilibrium Casimir force. Yeah, please.
Yeah, thank you. So thank you very much for the invitation, and it's my really great honor to talk here. I visit this institute this afternoon. It's very beautiful, so I hope I can come here very often afterwards. Okay, so today I'm going to talk about our recent work, actually, about the Casimir force, which is a classic topic in physics. But I will talk two parts. First part will be so-called equilibrium, and the second one, I will go to the non-equilibrium case. So the work, all this series of work is published, and if you are interested, you can go to the reference. I list it here. So first, I would like to introduce to you my collaborators on this series of work. So Guangle, he's a postdoc of us, and Rudy and David, they are my long-term collaborators along this research direction for Casimir force. So this is usually how we work together at the office. Okay. So I will, because this is a mathematics institute, so I think I will maybe give a little introduction to what is Casimir force at the beginning. The take-home message after this talk is that basically Casimir force is very general in physics. There are two necessary conditions for generation of Casimir force. One is as long as you have a correlation, a long-range correlated fluctuation. The fluctuation could be quantum fluctuation, or it could be stochastic or thermal fluctuation. As long as you have a long-range correlated fluctuation, and then you introduce the second condition is you introduce constraints into the fluctuation, then effectively you get a Casimir force between the constraints. So this is a take-home message. And then I will go to my first part is equilibrium fluctuations. The so-called equilibrium means that fluctuation will satisfy Gibbs-Boltzmann distribution or measure. So as long as you have Gibbs-Boltzmann distribution, you know that you can calculate the partition function and then the free energy. And by taking derivative of free energy with respect to a distance, you can end up with a force. So I will tell you a story of our development for calculation of partition function in terms of path integral method. But in particular, I will tell you a model which is an action in the path integral. This action will have to include a higher order derivative in the action, and this will lead to new physics. And then, because we can get the exact solution of this path integral, we then use this exact solution to study the so-called thermal Casimir force within the fluctuations of higher derivative order. So the second part, I go to non-equilibrium, which means that from driven, I will drive the system by external field. Then the fluctuation no longer satisfies Gibbs-Boltzmann measure. In this case, we don't have a partition function of free energy. Then how to calculate a force is a challenge. So we would like to follow a dynamic route to calculate it, which means that we will follow the dynamics of particles trajectory, and we will use a so-called Dean-Kawasaki dynamics to solve the problem, and then calculate the so-called correlation function, then construct the stress tensor, and the Casimir force is calculated in that way. So last, I will give an outlook, which is going to be my interest in the last 2 years, for example. So, which is, I would like to use this so-called Dean-Kawasaki method to study the stochastic thermodynamics, but for fields, not for Brownian trajectory, so to say. Okay, so this part will depend heavily on the technique, the so-called technique of Martin-Cigi-Ross-Jensen functional integral in order to calculate a path measure. So we have to use this method to write a path integral for a trajectory of fields. And then we can study the so-called fluctuation theorem, which is a central topic in stochastic thermodynamics. Okay, a bit on the Casimir physics. So to talk about Casimir force, we have to start with van der Waals. So we know van der Waals, actually, van der Waals introduced into the equation of states for ideal gas, two terms. So the first part is include a part which is the size of molecule, and the second part is the interaction between two molecules. So the molecules are neutral molecules, there is no charge. But van der Waals said that there is an attractive interaction between these molecules. This will trigger the condensation phase transition, which means the gas phase will go to liquid phase by this attraction between molecules. So this theory is very successful. So this is a comment by Uhlenbeck. He said that van der Waals' equation of states was so successful that it stopped the development of liquid state theory for 100 years. So it's too successful. But actually, there are some mistake, not mistake, something is missed. That is in Deutschland, some physicists did experiments on colloid suspension. So for colloid particles, if you calculate the interaction between two colloid particles, you find that the interaction force not follow this R inverse 6. This is van der Waals interaction, but it goes not this -6 law. Instead, it follows this R -7, so it means it decays faster. So what is the reason? So the physicists conjecture that this must be due to the relativistic effect. The reason, the argument goes like this. So the colloid particle, the size of colloid particle is in micrometer, but the molecules we know it is in aster. So colloid is much larger than molecules. So if you talk about interaction between colloids, so the characteristic length between the colloid particle is in the micron. So this length scale is already larger than the characteristic length scale defined by the velocity of light. So we know the force is not instantaneous. In order to have a force between two objects, there must be some message exchange. So this takes time, and light have a finite velocity. So this is the so-called relativistic effect or retarded effect for the interaction between molecules. So Casimir and Poder, Casimir is also a Dutch physicist. At that time, he picked up this problem and collaborates with his colleague Poder. He finished this calculation, and in fact, he found R-7 is the right physics for considering the retarded case of interaction between molecules. Afterwards, Casimir is not satisfied with this calculation because it is too complicated. So he always wants to find a simple route to explain the right physics. So when he visited Copenhagen, he taught this new work with Niels Bohr. And Bohr mentioned that that is nice, that is something new, but he mumbled something about this must be to do with zero-point energy. So this is all Casimir need to go forward to formulate a new theory. So then Casimir began to talk about, to look into the problem of zero-point fluctuation of vacuum. And then he introduced two macroscopic plates. The macroscopic means he wants to remember he is motivated by colloid. Colloid is a macroscopic size object. So he put two macroscopic body into a vacuum and calculate the interaction between these two plates. That leads to the so-called Casimir force, which now is very famous. But afterwards, actually, his work was generalized by Lifshitz. So this Lifshitz is the Landau-Lifshitz. So they wrote 10 volumes for theoretical physics. Every physicist would have to read through. And But in his 10 volumes, this Gensval has a comment to say that Lifshitz calculation was so cumbersome that they were not even reproduced in the relevant Landau-Lifshitz volume, where, as a rule, all important calculations are given. So it means that the calculation is too long, it's too tedious, so they don't even want to include it in a book. But what Lifshitz did is that he generalized for Casimir, the two plates are ideal metal, which means that the polarization is ideally polarized. But Lifshitz went to consider the real materials. So instead of ideal metal, he used the true material, and the medium is no longer vacuum. So he has to worry about the polarization and the interaction. So eventually he used the so-called fluctuation dissipation theorem to finish the calculation. And now Lifshitz theory is sort of a model to calculate the interaction between real materials. So now this is a bit on the history. Now I will give you a very simple introduction to follow Casimir's arguments. Okay, so Casimir looked into vacuum, and we know that vacuum is full of electromagnetic fields, which can be decomposed into a set of harmonic oscillator. So the energy spectrum of harmonic oscillator goes like this. This is from any textbook of quantum mechanics. The N is the index of mode, E is the energy, and h bar omega, omega is angular frequency for the mode. So this is just the eigenvalue of a harmonic oscillator. And now we go to vacuum, which means that we go to the ground state, which means there is no quanta in this system, so N has to go to 0, so we end up with this ground state energy for the harmonic oscillator. But from quantum field theory, we know that the quantum system has to satisfy the uncertainty principle, which means that the quantized field has to consist of all the oscillators with all the frequencies. So in order to calculate the ground state energy, you have to sum up with all the frequencies, with all these frequencies whose angular frequency is omega. But if you finish this calculation, because you don't have a cutoff, you don't have a regulator this is infinite series and it diverge. Okay, so the result is that the vacuum energy is divergent. So how can you get physics from a divergent object? This is renormalization. We know today we know that very clear. But at Casimir's time, what he did is he had this insight. He said that well, if I introduce two plates into the vacuum, so the existence of the two plates will perturb the fluctuation of the vacuum electromagnetic fields, which means that the fluctuation spectrum will be modified. So remember the K is the wave vector, wave number of the modes. So the K will be modified into this form. A here is the interplate depth. So again, if you sum up with all this frequency, again you get a divergent object. But the interesting thing is that if you subtract this divergence by the divergence in the free space, you end up with a finite Casimir energy. As long as you have a finite Casimir energy, you can just perform a derivative of that finite energy with respect to the distance a, like here, you can end up with a Casimir force. So this is what he found in 1948 in his celebrated paper, very, very short paper, only 1 page, I think. And so what he found, what is interesting is that first, this force is attraction. It is attractive force between two plates. Remember, this is in vacuum, okay? And the two plates are ideal metal and no charge. So the force can only come, that of course we don't worry about the gravity here. So the only reason the two plates attract each other is because vacuum fluctuation. And it is attraction also, it is a power law, which means that there is some universality here. This constant here is independent of the details of the metals. So this is so-called universality. Actually, the the power of 4 here, -4 here, is universal, we can just get this result from very simple dimensional analysis. If we notice that this is a, this is a relativistic calculation, so we have to have a velocity of light, and also this is quantum fluctuation, so we have to throw the Planck constant there. So h bar c gives us a length to fourth order. So in order, we have to have okay, this is the pressure. So this guy here gives us a energy multiply length. So in order to have a pressure, we have to have a fourth order of length. So this is actually Casimir's calculation. And then physicists notice that in Casimir's calculation, the important thing is that he has a fluctuation which is electromagnetic fluctuation. In quantum field theory, this corresponds to a photon. A photon is massless, so it means that the fluctuation is long-range correlated. So as long as we have a long-range correlated fluctuation, then we can introduce some constraints like 2 plates or something into the fluctuation. Can we get a Casimir-like force? So this is how the argument goes. Then in 1975, 2 physicists, statistical physicists actually, Michael Fisher and Dean, they proposed that in physics, that time, in 70s, one topic in physics which is very popular is critical phenomena. So people want to study the critical point. At the critical point, fluctuation actually, the correlation length goes to infinite. So this is typically a long-range correlated fluctuation spectrum, fluctuation medium. So whether we can study this critical point and find Casimir-like force. So Fisher and Dean did the calculation, and basically this is their model. Phi is the so-called order parameter, which you can understand it as the density distribution of your liquid. And then the Hamiltonian just goes like this, the gradient phi squared, so we don't have a mass term here. So this is typically at critical points, the mass goes to 0, so we have a long-range correlated fluctuation. Indeed, critical Casimir force was predicted by them and confirmed afterwards by experimentalists in Germany, I think. And another thing, another category is that, well, we know that critical point is very special. You have to fine-tune your experiments and to reach the critical point. But can we find other conditions to generate the similar physics? So it arguments like this: if instead of a scalar field phi here is a scalar field, if we use a vector field which can rotate, then if the system undergoes a phase transition, we know this is a very typical Mexican's hat. The phase transition, the disorder phase will be here, and after phase transition, the system will go to one of the minimum here. But there is a loop here because you have a rotation symmetry. But at different position, if you want to go from this guy to this guy, you don't cost any energy. So this means that the excited particle is massless. Again, this gives us a long-range correlated mechanism. And actually, this is the so-called Goldstone mode in high-energy physics, also in statistical physics. This guy can also give us very similar Casimir force. For example, in superfluids, in helium-4, in a very thin film of helium-4, people actually measure the depth of the film, and when the system undergo a phase transition, they observe a drop of the depth, which is attributed to the Casimir force, actually. And also, of course, this guy, if you treat phi as electrostatic potential, this is a typical electrostatic Coulomb interaction. Again, it's very similar, right? So it can also have very similar physics. And another very very widely studied topic nowadays is in non-equilibrium statistical physics. The reason is that if we have dynamics, for example, the dynamics of density evolution, because the total density must be conserved for our system, so this gives us conserved dynamics. This constraint will enforce a long-range correlated fluctuation. So that's why non-equilibrium statistical physics began also to look at the Casimir force. So I will, in a summary, because we want to have a long range. Why we want to have a long range? Because long range force can smooth out all the microscopic detail and give us universality. And as long as we have universality, we can use scaling argument to directly give us physical results. Like this is the so-called generalized Casimir force. Note that we don't have H bar here. We are no longer talking about quantum fluctuation, but thermal fluctuation. So we have a KBT, which is the typical thermal energy, and we have a length, which is the distance, and then we can then get the generalized Casimir force. Okay, I will give a summary. So the notation, the take-home message is that as long as you have a long-range fluctuation, which can, in quantum field theory generated by gauge symmetry, we know gauge symmetry give us massless particles, and massless particles give us long-range power law, then have a universality like Casimir did. In statistical physics, again, we need a symmetry to give us a massless particle, which will correspond to the scale invariance in critical point, or the Nambu-Goldstone particle for the vector field. And again, we have the similar physics. And also, if we drive the system to non-equilibrium case, conserved dynamics give us long-range power law, and we can. Okay, this page will give us the so-called Casimir physics, how to study Casimir physics. As long as you have a symmetry and you have constraints, you can study, you can calculate. Okay, now I will move to my our work on this topic. The first part is equilibrium fluctuation. I mentioned to you that means that fluctuation satisfy Boltzmann distribution. So the point is that as long as we can calculate the partition function of the free energy, we can end up with the force. So how to calculate the partition function? Effective way goes like this. Like this is the partition function. So we have a field x, and S is my action or Hamiltonian. So this is just the partition function. This guy is a Boltzmann distribution for the fluctuation xs. So we can first fix the 2 point endpoints x and x prime, like write it in this way. We use two Dirac delta function to fix at time t0, we fix it at x, and at time t we fix to x prime. Then we end up with this so-called Feynman path integral. And after we calculate this guy exactly, we can then integrate out all these endpoints, so we can calculate the partition function in this way. Two-step, okay? So we will point out that here you can notice that the state variables so for this calculation is x, the big xs will correspond to, this is xs and the first derivative of x to s and the second and this guy. So depending on your action. So remember, look, this action is written in a quadratic form, but the quadratic form for x, s, and the first derivative and second derivative, and all the way to the n-1 derivative. So this is sort of a generalized quadratic model for the Gaussian fluctuation. Why we do this type of generalization? The reason is that if we take just n equal to 1, this will give us, in mechanics, is just give us harmonic oscillator. In phase transition study, this exactly gives us the so-called Landau-Ginzburg-Wilson model, which describe the liquid-gas phase transition and all this type of phase transition very well. And in stochastic process, this guy gives us the so-called position space Brownian trajectory, and so this is well studied in textbook. But if we include another term, which is the second order derivative here, n is equal to 2 here, then it means that we are talking about a model which is called the Brodowski model, already beyond the Landau-Ginzburg-Wilson Hamiltonian. And of course, in stochastic process, this is a velocity space Brownian motion, and this path integral already has been calculated by Kleinert. Kleinert is a theoretical physicist in Germany, and he wrote a very famous book for path integral, very deep. And in his book, he actually includes this result, but it can be found by us. This can be calculated by us again, but we use a very sort of simpler method to get the same result. But we can go further to the third order. This means we add another term in the action, and this will correspond to the acceleration space Brownian path. For other topics, there are also some other use, but this is rarely discussed. And we can even go even higher order, so up to the physical context. We can actually first construct this action and do the calculation for the path integral. So one comment here is that higher derivative term actually take care of the non-locality effect in field theory. We know field theory is built on the locality principle because the light has a finite velocity, so the field theory is a local field theory. But sometimes we want to worry about the non-local effect in field theory. How to proceed? One way is just to include higher and higher order derivative of the field. Okay, so how to calculate the path integral? We know that that is a functional integral, so it is an infinite dimensional object. It's very hard. Like Feynman tells us how to discretize the space and then do the summation. But another way is just to go directly to the PDE. Okay, that is to say we use this so-called Feynman cut formula and to find that the path integral satisfies this PDE. And this PDE is composed of two parts. The first part is just a stochastic process. G dagger is the generator, self-adjoint generator for this stochastic process. And V means that the trajectory is traveling in the presence of external potential. Okay, I wrote it down. Use Ito's calculus. This corresponds to a Ito process, which is the first part is a noise, Ito noise, and the second part is a drift term. And once we have that, we note, or we also, now we want to solve this equation, but we want to use some ansatz based on we have a path integral corresponding to a quadratic action. So we want to make this Gaussian ansatz. So we see, why not we just substitute this guy? This guy is K, is exactly a Gaussian function, a quadratic form. And then our unknown object will become A prime, and B, which is just the coefficient for the endpoint interaction between the endpoint, and also a prefactor, which will be the functional determinant. But once we substitute this ansatz into the PDE, we end up with a quite nonlinear equation, so we cannot actually solve it. So okay, lead to nowhere. But also, of course, there is some other progress along this direction. For example, the functional determinant is related to this term, this guy here, which is a so-called Pauli-Van Vleck-Moret formula, which is also a very important work to calculate the functional determinant, which will correspond to the so-called one-loop calculation in field theory. Okay, but how to go out, because it's nonlinear, we cannot solve it. So what we did is that we noticed the diagram here, like this guy, this x to t travel from x to x prime. This is Feynman propagator. We want to solve this guy, but we don't know it. But what we can do is we can just add two parts from t to infinite and from minus infinite to 0. So the whole thing will become this guy. So this guy will be a so-called Gaussian random field theory. This is well studied in statistical field theory. So we have the solution of this guy, which is written down here. Okay, this is a Gaussian random field theory, or the so-called unconfined path integral. And in order to have this guy, we add two terms here and here. But these two guys, because the time here is infinite, so we can invoke the so-called ground state dominance approximation. So we can write the solution for these two parts also, which is basically a Gaussian. Okay, which is basically Gaussian. So we put them together. We have this guy, this guy, this guy. So we can solve for that. So we end up with the exact solution for a path integral with quadratic action, but including higher order derivative terms. So this is the detail. I will not point out here, but the most important thing in this calculation is that we have to calculate these two matrices, SR and SL, which is a renormalized surface correlation matrix. Okay. So some general structure of the solution. So we observe that for this renormalized correlation matrix, they have some relation with the correlation function for this Gaussian random field theory. And also there is a term mu, which is basically you see this is basically the ground state energy. And if we take n equal to 1, we recover the well-known results in Feynman's textbook, but using our machinery. And we can go to n equal to 2. We recover this. This is a very huge formula. It's ugly, right? It's very ugly formula, but it's already obtained by Kleinert in his book. But now, using our method, we can get it sort of quickly. And also, this result is included in this book. And of course, we can go to n equal to 3. But now, because we have the path integral for this, how many times? Let me see. Okay. We can just use this obtained exact result to study the so-called thermal Casimir force, which means that we have the path integral. Path integral is sort of a partition function of the fluctuations. So n equal to 1 corresponding to the fluctuation for the Ising model. Ising model, in statistical physics, Ising model is a very basic model. The Ising model is the Hamiltonian to describe the fluctuations. Energetics is this guy. So we have the gradient phi square, which basically take into account the inhomogeneous of the system, and this guy give us excitation. The P naught square basically is the mass of the system. So this is a Ising model, and when P naught square goes to 0, the system undergo a phase transition and transit from a disordered phase to a ordered phase, macroscopic ordered phase. And if you plot the so-called fluctuation spectrum, the gamma q is energetics of the mode q, and q is the wave number. It is monotonic equation, monotonic curve. And the soft mode, which is the mode has the least eigenvalue, is q naught equal to 0, and the q is wave number when q goes to 0, which means that in real space it is long wavelength fluctuation. So the long wavelength fluctuation will trigger the disorder to order phase transition Ising model. But if you include another guy, like this guy here is only first order derivative, but we have second order derivative here, then the energy spectrum changes to this guy. So it is no longer monotonic, but it has this part here. So this part turns out to be very important. It changed the phase transition scenario totally. Like if you go to the fluctuation mode space, what you notice that the soft mode here is q naught equal to 0, but soft mode here is q naught not to 0, but take a finite value. So it means that there is a spherical shell here. So for q is less than q naught, which means this part it is long wave fluctuation, but for q larger than q naught, it is so-called short wave fluctuation. And because the existence of this shell, the phase transition is totally different. It leads to a different universality class for phase transition. So we want to study the Casimir force when we're confining this n equal to 2 fluctuations. So I will tell you the first thing I want to point out is that when you go to the higher order derivative terms in your action, you can play with the boundary condition, because now not only you have x dot, but you have also x second dot. So you can enforce the boundary condition in x and x dot, okay, altogether. So you have more choice of boundary condition, like I list it here. So different boundary condition corresponding to different constraints. So different constraints will give you basically different Casimir interaction. So the interesting thing is that by playing with the boundary condition, whether you can find repulsive Casimir force. Remember, Casimir force is attraction. So if we play with the boundary condition, can we find a repulsive Casimir force? That is the focus of this work. Okay, I think I skip this part. This is just I take a Robin boundary condition, which is a typical boundary condition, and I finish the calculation. The important thing is that now, remember, this is an equilibrium calculation. So our object, what we want to calculate is the free energy. So now the free energy is the sum of all the modes. The mode Q, the Q is the in-plane mode, and because we have this spherical shell here, so we should classify the mode into two types. The first type is the short wavelength, which is Q is larger than Q naught this part, and the other guy is the Q is less than Q naught here. So if you only take into account the short wavelength modes, you will end up with very similar results as Ising model. Only when you take into account this part, you have this new term here, and this new term gives you very interesting physics, which means that it will give you an oscillatory Casimir free energy. Once you have oscillation here, it means that you have many, in physics, it is called the metastable states. You have many metastable states, so you can play with the system. For example, the free energy is here. You take derivative, you get Casimir pressure. You see that Casimir pressure can be positive or negative, and even there is some many zero Casimir force. So why you have this type of behavior? I want to point out is that the reason is we go to second order theory. If we only stay at the first theory, the calculation will only give you a monotonic curve, which is a Casimir attraction. Okay, so I list the main result here. The interesting thing is here. You see that this is the Casimir amplitude. So when it is positive, it means repulsive interaction. See, we have some repulsive interaction here. So if we take the boundary condition as Dirichlet and the Neumann boundary condition, we can have a repulsive Casimir force. And this part, equilibrium calculation, the importance is that we basically generalize the so-called critical Casimir force into a new universality class. By doing that, one thing that we find a lot of metastable states. The second thing is that the Casimir force is in a longer range. Remember, the Casimir force in the critical Ising model, it goes like h to the third order. But for this, including this higher order derivative, we have h minus 1. So this longer range. So it should be, in some time, it should be useful to detect in physics. Okay, so I think I go to the second part here. Second part is now I want to drive my system out of equilibrium, which means that I will through enforce an external field, I will break the detailed balance in the system. Then once the detailed balance is broken, the fluctuation is no longer satisfying a Boltzmann distribution. So in this case, I don't have a partition function, because partition function basically is the sum of Boltzmann distribution. I don't have a Boltzmann distribution, then I don't have a partition function. Of course, I don't have free energy, so I cannot calculate as in the equilibrium case. So how to calculate? I just follow the dynamics. Okay. For example, I construct a very similar Casimir geometry. This is two plates, but between I don't have a vacuum. Instead, I have electrolyte solution. So this is plus and minus ions flowing in a solvent, and I have confining plates in here. So this is very similar to Casimir setup, but different. This is a statistical physics setup. And I want to start with equilibrium calculation, which means that I first, this E is the electrostatic field. When E is equal to 0, the system will relax to a Boltzmann distribution. So I start with a Boltzmann distribution. So Boltzmann distribution calculation will goes like, again, I can calculate a partition function. In this calculation, I actually use a field theory, which means that I will describe the two plates by a polar field, and the ions by a so-called the electrostatic potential field. And then the partition function, this is again the Boltzmann distribution, and I have, this is the Gaussian model. So I can calculate it out, and also there is one important thing is that in this calculation, I have to have a time scale separation, which means that the time scale of the two plates is much shorter or the much shorter than the ions. So this time scale separation means that I can develop an effective field theory, which means that I can integrate out fast degree of freedom and just focus on effective theory, which is only include the so-called slow degree of freedom. Okay, so if you finish this calculation, the most important thing is that you will end up with the total force between the two plates is read like this guy. So this is an exponential decay force, and h is the distance between the two plates. Kappa is a length scale, inverse length scale. So once h is very larger, once kappa h is very large, the force will decay to zero. So this is the so-called screening, which is also an important effect in physics. So the important thing is that in this calculation, once I take the two plates far apart from each other, I don't have any Casimir force between the two plates. Now I begin to drive the system. So I want to see if I drive the system out of equilibrium, can I have a Casimir repulsion between the two plates? Okay, so then I drive the system and do the dynamic calculation. So you know, in the presence of electrostatic field, the ions will move. Like ions will move in this direction. Positive ion move this direction, and this guy moves in that direction. And I can focus on the Langevin equation for each ion. This is the overdamped Langevin equation. And but because I have many ions here, so I have a lot of SOD here that cannot be solved analytically. So what we have done is that instead of focusing on each ion, we go to a description in terms of field. So we define a density field ρ here. Basically, the ρ is a sum of Dirac delta function. Each Dirac delta function will tell us whether this ion fall into position X. So this is the density operator. Note that this guy is not averaged. So it is again still it is a random variable. It is not under ensemble average. So it is again a random variable. Its randomness comes from xi, and xi's randomness comes from eta I. So this I just change a distribution language, define a new random variable, and use Ito calculus. I can actually perform an exact derivation to find what is the evolution equation for this random variable ρ. Ρ is the density. Okay, I found that the equation is looks like this. So this is this is called the Dean-Kawasaki equation. Dean and Kawasaki are both two physicists who found this equation, and you see that this equation is basically a Langevin equation. So if you treat ρ as a random variable, this is the rate of change of ρ, and the first part is a drift part, so a Hamiltonian with respect to ρ, and the kappa is a mobility operator, and also you throw in noise into your Langevin into your deterministic equation to make it a stochastic equation. And how to enforce noise? The noise cannot be enforced arbitrarily. Noise has to be fixed by the Brownian motion here. So if you follow the Ito's calculus, you will find that the noise for the density operator here has to satisfy this equation. Here D hat is the so-called diffusion operator. Diffusion operator and this mobility operator will satisfy the so-called fluctuation dissipation theorem. And then another thing is that what is your Hamiltonian? The Hamiltonian will guide your dynamics to the minimum of the Hamiltonian. So what is the Hamiltonian? The Hamiltonian goes like this. So the first part is ρ log ρ. We know this is basically the entropy part. And we have a two-body interaction, ρ, and G is the interaction kernel. And also we have ρ interact with external potential. So basically this is an effective Hamiltonian or effective free energy, because this is entropy and this is energy. And also I can write it in another form, which is more interesting in nowadays, because this is basically a relative entropy or a KL divergence. Because I can write it in this way, I can define a steady state distribution for rho. Then I put it in this form, which is a relative entropy. We know the relative entropy is a convex function, like this convex function. So if we follow the dynamics guided by this convex KL divergence, we will in a long time we will evolve into this rho st steady state. So this means that we have a sort of Lyapunov dynamics for our SPDE. Okay, of course you can also stress this dynamics because this dynamics is for density operator, so it must be a conserved dynamics. So you must be able to write this dynamics into this divergence form, gradient structure, divergence of a current. But note, because the rho is a stochastic variable, so this is no longer Fock-Planck equation. Okay, in Fock-Planck equation, we only have the first two terms. The first part is diffusion, and we have drift part. Now, because the rho is a stochastic variable, so in the current we have a stochastic current, which is the d hat is here. Okay, so this is the structure of what I used to solve this type of non-equilibrium dynamics problem. But the difficulty of solving this equation is lies in that first is that this noise zeta here, d hat is dependent on rho. Rho is our so-called state variable. So the noise depends on the stochastic variable, which means that the noise is a multiplicative noise. So usually multiplicative noise is more difficult than additive noise. You have to be careful with the stochastic integral. Use Ito or Stratonovich or use other calculus. And the second thing is that there is a rho here, and there is also a rho here. So in mobility and force, we both have rho there. So this is a nonlinear PDE. So nonlinear PDE. Okay, you cannot solve it. Okay, how to do that? For physicists, this is sort of a standard route to go. As long as we run into a nonlinear equation, the first thing in our head is we want to linearize the equation. So we linearize the problem. Okay, how to do that is we do a perturbative expansion. So this is our density operator. We expand this density around average density. So we end up with a fluctuation of density. Now we keep all the expansion into linear order of the fluctuation. Then we end up with the same equation, but in this time, this Dean-Kawasaki equation becomes linear. And we enforce boundary condition, which come from the two Casimir plates, and we also do the mode decomposition by Fourier transformation. And in the Fourier space, the equation, the PDE actually becomes this sort of like a very simple equation, and we can what we want to calculate is the correlation function of the fluctuations. So the correlation matrix is our interest. Once we have the correlation matrix, I mentioned to you we don't have free energy, but what we have to calculate is the correlation matrix. Once we have this guy, we can actually calculate the stress tensor. Okay, so we write it in this matrix form. This is sort of like linear form, and basically it is an OU process, and we can solve it. And this ugly formula here, but it's not important. The important thing is that finally we can calculate the stress tensor here. You know, stress tensor can give us force. The stress tensor is composed of two parts. One part is osmotic pressure, and the second part is just the Maxwell stress tensor. And finally, the total force, we can calculate it out. And this is the final result here for the calculation. But we want to check our theory whether it works or not. So the first thing is that we take the electrostatic field goes to 0. So in this case, we know that we take out the driven. So the system, the calculation should reduce to the equilibrium calculation. Indeed, when we take E equal to 0, we recover the result obtained by the free energy calculation. So the dynamic calculation gives the same result as the free energy calculation. And the second more important thing is that we drive the system. So we take a E, and this is the final formula here, but we want to study the long-range limit, right? Because Casimir force is the long-range force. So take the long-range limit, we have this formula. if we plot it out, so Ft is our Casimir force, and H is the distance between the two plates. So note that G here is the electrostatic field. So this plot is this axis is the distance between two plates. So for G equal to 0, which is the equilibrium calculation, so you see that in the large H, long range, you have 0 force. But then you turn on the electrostatic field, you have a repulsive force, and the repulsive force actually goes increase when you increase the electrostatic field G. But it will plateau when G goes to very, very large. It will no longer increase. Okay, it has a large limit, upper limit. And the other plot is when we can fix one distance between the two. We can fix two plates and just increase the electrostatic field. And the result is that again we see that this guy is actually is very small, so it's always attraction. But if we increase H to like to here, H to 2, we can, when we increase the electrostatic field, the force can change from attraction to a repulsion. And in the long range, actually, the force can change from 0 to a non-zero repulsive interaction. So this is the most important finding in our dynamic calculation. So as I told you that we have a repulsive interaction, which when you don't have a driven in your system, it is 0. So now what is the physics behind this calculation? Actually, it is very intuitive. We can imagine it. I put a cartoon here. This is my fluctuations of ions between the two Casimir plates. So if I don't drive the system, the plus ion must accompany with this minus ion. They must travel together. So they are 1 degree of freedom only. This 1 degree of freedom, if you calculate, you will find this will contribute a repulsive interaction between the two plates. And the van der Waals interaction between the two plates is attraction. So this degree of freedom cancel exactly the attractive van der Waals force. This is why in equilibrium case you don't have a interaction. But if we drive the system, the plus ion and the minus ion travel in different directions, so they are no longer 1 degree of freedom. They change to 2 independent degrees of freedom. So each degree of freedom contributes a repulsion. 2 minus 1. So this gives us the attractive repulsive interaction here. So once we notice this intuition, we can devise our system. We can put more degree of freedom. Like n is my degree of freedom, which means we have different species of ions in the system. So we can increase n. We can increase the strength of repulsive interaction. So we can sort of like, if we want to have a stronger repulsion between the two plates, we just put more ions in the system and increase the electrostatic field to very large value. And also along the direction of this study, we also find a very sort of like a method to reduce the Lyapunov equation, because Lyapunov equation describes the steady state correlation function. So we have to solve it to get the stress tensor. But we found that we can actually simplify the Lyapunov equation's solution. Okay, I will. Okay, the last part is just outlook. So because recently my work focused on this the Dean-Kawasaki stochastic PDE actually, or for physicists is the stochastic dynamic field theory. So I want to use this dynamic field theory to study the same stochastic thermodynamics, which starts from, for example, in Japan, stochastic thermodynamics is very developed. Many people work on that. Also in America, Jarzynski worked on this, and Crookes worked on this since 1990s. But all those works focus on Brownian trajectory. So it's only one trajectory. You look into the trajectory, forward trajectory and backward trajectory, and you calculate the ratio of the path probability, you end up with entropy reduction. But now, because I already defined a new random variable, which is my density operator Rho, so I want to, go forward trajectory for the Rho and the backward trajectory for the density Rho, and also, of course, I can calculate the entropy reduction. But this time, it is for many body interacting many body Brownian particle system. So it is no longer one trajectory, but many trajectories interacting with each other, but use my new Dean-Kawasaki dynamics to calculate it. So some methods, for example, I can also take into account the so-called non-Gaussian effects by just using this technique, Martin-Cigi-Rose-Jensen technique, and also the entropy production basically can be obtained by analyzing the symmetry of action, and this will lead to a bunch of new fluctuation theorem for fields actually in the field level. That is all I want to report to you today. So thank you for your attention.
Very much, Professor.
Thank you.
Miao. So are there any questions?
What does this T mean?
T means total. T means total force, because the force is decomposed into several contributions. That it comes from van der Waals force and from the ions fluctuation. So I have to add them together to get a total or net force.
So I would expect if you start with this non-equilibrium and then you wait like time go to infinity, they will go to this equilibrium.
Exactly. Yeah. So, but you have to let E go to 0. If you always drive the system will no longer relax to, it will relax to a steady state, but the steady state is no longer an equilibrium state. Because you drive the system, you break the detail balance. You will always have a current in your system, even you run an infinite long time.
And maybe I wonder that's whether this method can apply to study these black hole, those stuff. Is the
Yeah, that will be very cool stuff. We should talk maybe afterwards. We can talk together. Yeah.
Any other questions? No. So yeah, thank you very much. Very interesting talk. So very suggestive talk. So there are many things which many terminology which I know, but I'm a mathematician, so
yes,
so that maybe I couldn't understand totally some essential part. But for the Dean-Kawasaki case, did you take? So you in the first part you talk about some higher order term.
Yes.
Then the Dean-Kawasaki, did you take?
Exactly. That is exactly what I. Next step, I will.
Next step, I see.
In the
at the moment, you just take a first order term.
Yes.
I see.
Yes. That will. I believe that will lead to new interaction in the non-equilibrium Casimir force. New scenario. Yeah.
Okay.
Yeah.
So many other things. For example, Robin's boundary condition also appears in mathematics. So maybe there are several.
That's right. I also discussed with Zhang Qi. He also told me a lot of because I'm a physicist, so I don't know that that type of mathematics. But he told me that if you put higher order derivative into your Hamiltonian, and this Hamiltonian will lead to somehow better defined dynamics or something. It is compared to Ginzburg-Landau, it will more smooth or something. I don't know how. That's right. Yeah. That's right. That's right. That's actually we can look together. Actually, that is also I want to calculate is what will be modified, what the entropy production will what is the entropy production in this higher order derivative action. Yes. Yeah, because the first step is you define it pathwise, right? You can just that is SPD, but use this trick, you can write it as path integral, and you can have action, and you just reverse time. You can calculate the ratio between the path probability, and it, of course, will give you an entropy production.
For this situation, so that means we can only define the entropy production for the stationary.
Yeah, that's a subtle problem, actually. That is quite subtle. Yeah, you are right. Maybe because that is, I believe we are talking about the endpoints, the initial time distribution and the final time distribution, whether they need to be a stationary probability distribution or not. Yeah, I have to think about it more. Yeah, maybe, you know, I collaborate also with other people, mathematicians, on this transit, not stationary fluctuation theorem. But I have to think about how to adjust, how to, you know, this calculation how to fit to my new work there. But yeah.
Okay. Any other questions or comments? Okay, so let's thank Professor Miao.
Thank you.
Interesting
Thank you very
talk.
much.
Thank you very much.
Yeah.